ready to kick things off with 1.2.
Greatest common factors and least common multiples. We can use prime factorization as a means to find the greatest common factor, or GCF, and least common multiple, or LCM, of a group of numbers.
So the greatest common factor is the greatest number that divides into each number in a given set. So for example, 5 is the greatest common factor of 10 and 15. The least common multiple is the lowest whole multiple that is the same for each number in a given set. So again, if we're looking at 10 and 15, the least common multiple will be 30. Okay.
There are a whole bunch of ways to find greatest common factors and least common multiples. We're going to show you some ways to do so. These methods can be handy, but if you have other methods that you prefer, that is certainly acceptable. One thing we can look at is a Venn diagram. And Venn diagrams can help if we break down the numbers into their prime factorization. So if we look at 12 and how it's 2 times 2 times 3, we look at 30, how it's 2 times 3 times 5, we can use a Venn diagram to sort out their factors. So there's a 2 in common, hence that. Alright, we've taken care of that. Then 12 has another 2, but that's not part of 30, so there it goes. Then there's a 3. Oh, that's in both. There's a 3 in both, so that goes in the middle. We've taken care of that. We've taken care of all that. And all that's left is this 5, which is part of 30, but not 12. So here's that, turning it into a Venn diagram of factors. And what we see in there is if we just look at this circle, if we multiply everything in there, we'll get 12. If we multiply everything in this circle, we'll get 30. What's interesting here is that we have this common area. And that's everything that's common to both. That little section gives us the factors of the greatest common factor. If this is everything that's common, then we can multiply that so that we get the greatest common factor of 12 and 30, which in this case is 6. If we want the least common multiple, then what we want is to include each one of these once. So our least common multiple is 2 times 2 times 3 times 5. Everything we see in here. And when we multiply that out together, we get 60. So that is our least common multiple. And we can use Venn diagrams in these examples.
So for this first one, we have 2 numbers here. Our first number is that, written in expanded form, prime factorization. And the second one is this 2 times 5 times 5 times 7. We are going to kick things off by drawing a Venn diagram.
Nice circles.
Thanks.
You freehand those?
Yeah.
Pretty impressive.
All right. So I'm going to start by filling in my middle. So my middle includes everything that they have in common. So here I have a 2 and a 2 in both of these numbers. So I'm going to put a 2 in the middle. For this number here, I'm going to just draw arrows so that you understand which circles relate to which numbers. What else do I have in the middle? Well, I can see that each number has a 5. In fact, it has another 5. And that's all. That's all they share in common. So to finish off this first circle on this side here, relating to this number, I'm just going to include all of the values that are not in the middle. So I'm going to have the 2. Oh. I'm going to have the 2, the 3, the 5, and the other 5. And for this second number over here, I'm going to fill that circle with what's remaining, which is just this 7. So, if I wanted to determine the GCF I would include everything that is common between those two values, which happens to be the 2 times 5 times 5, or I could write it as 2 times 5 squared. Notice that in the instructions it says that I could leave my answer as a product of prime numbers. I don't have to evaluate. Oops, got rid of that square right there. But if I wanted to, I could. So if I wanted to find the GCF, I would just go ahead and complete this multiplication, and I could find the actual number. Okay. My least common multiple, or my LCM, I'm going to include every number in the Venn diagram once. So I'm going to include the 2, this 2, which is 2 times 2. I'm going to include the 3. I'm going to include this 5, this 5, this 5, and this 5.
So many 5s.
I know. And I'm going to also include that 7. Of course, I can go ahead and skip right to that power form. I don't have to write in an expanded form every time here. So I'm going to get 2 squared times 3 times 5 to the power of 4 times 7. All right.
I'm going to do an example too. I will do it the same way.
Whoa, twinsies.
But with different colors. Let's see what my freehand circle looks like.
Oh
Wow,
my
not bad.
goodness!
Yeah, I don't mean to brag, like...
Did you take the same seminar I did?
Probably. The real question is, can I just copy this? Oh, there's a duplicate button. I could just use that.
Dang.
Oh, look at that alignment. Free-handed. Yeah, I did that. Freehand. And put some numbers in here. So there's a 2 in both. Oh, that's it for the 2's that are in both. Okay. There's a 3 in both. There's 1. There's still another 3 in both. So that's another. There's still another 3 in both. Okay. And there's still another 3 in both.
Holy smokes.
Yeah, they've got a lot in common. They should be friends.
Aw.
And this first number on the left still has an 11. And this number on the right has another 2 times 2. So there's the Venn diagram of how this whole thing works out. So, if I want to look at the GCF, we're looking at this common area for the common folk, which has a 2 and a 3 and a 3 and a 3 and a 3. And we can write that as 2 times 3 to the power of 4.
Wow.
I'm just going to go ahead and evaluate that. Psych! I don't have to. The instructions say I don't need to evaluate. I need to leave my answer as a product of prime numbers. I'm out. Except for the fact that I still have to write down what the least common multiple is. And for that, accounting for everything in here, I've got 2, 2, and 2. 2, 2, and 2. I've got these 4 3s. So many of them. And then finally this 11 over here. And I can condense that just a bit. And there's the GCF and LCM of those numbers.
Nice.
Nice.
Whoa! Next question, we have 45 and 20. We can actually go ahead and do the same thing and still create the Venn diagram. We just have to get the prime factorization first. So my personal favorite method for prime factorization is a factor tree. So I'm going to go ahead and do that. So we have 45 as 5 times 9, which is, that's prime, and 9 is 3 times 3. So we have 45 being 3 squared times 5. And 20, whoop, whoop, we have 5 times 4, and 5 is prime, then 2 and 2. And those 2's are 2 prime. So 20, that's weird that the 20 cut out. 20 is equal to 2 squared times 5. So if I'm going to go ahead and make that Venn diagram, copy. How do you paste it?
Oh, his tabs are also on the screen. But try the duplicate button.
No, duplicate.
Ah, that's right.
Nice. Okay, and I'm gonna move these guys, I think. Methinks. Alright. So, I'm just gonna put that there. So, what they share in common here are these 5s. So let's go ahead and put the 5 in the middle. I think a very common mistake that people make is noticing, oh, this guy has a 5 and this guy has a 5, so we should put 2 5s in the middle.
That's madness.
Yeah, it is in fact madness because they share 1 5. They each have 1 5, so we only include the 5 once. Okay, and that's all they share in common here. The 45 still has 3 and a 3 left over. The 20 still has a 2 and a 2 left over. And those are all the values. So if I'm looking at my GCF is just 5. My LCM is going to be the 2 2s, 2. The 2 3s, 3 times 3. And the 5. Which can be rewritten as 2 squared times 3 squared times 5. Alrighty, Venn diagrams are awesome.
Yeah, they're pretty dope.
Do we always have to use them though?
Oh, what a question. Someone's been reading ahead in the notes. No, we don't have to use them. There are faster ways to do things. And they come from the exponential form or the power form of the prime factorization. If we look at these, bloop, blop, bleep, and the numbers we had here at some point, this one on the left is 2 squared times 3 times 5 to the 4. This one is 2 times 5 squared times 7. Over here, the GCF is 2 times 5 to the power of 2. Where does that come from? How can we possibly get that based on these prime factorizations? If we look at this real carefully, we'll notice that there are limiting factors. They both have 2's, sure. This one has 2 2's, but this one only has 1, which is why the GCF only has 1. This first number has a 3. This second number doesn't. That's why this GCF has no 3's. This first number has 5 to the 4. This second number has 5 to the power of 2. They don't both have 4. Really, the most that they can share is 2, which is why this GCF has 2 5's. And then finally, if we check out the 7's, this one has no 7's even though this one does, so 7 can't be something that's common. The GCF can be found by taking any of the common prime factors but using the lowest exponent we see on that factor. So where this was a 2 and a 1, this ended up as a 1. We ignored the 3's, but where we had a 4 and a 2 for exponents on 5, the lower one was 2. Operating on the other end is the LCM, and that uses the highest exponent we see on every factor, whether it's common or not. So how many 2's were there? The max was 2 2's, so we included 2 2's. This didn't have any 3's, but this did, so we included it as well, just to make sure that number is accounted for. How do I undo? Nailed it. We need some 5's, but to make sure both of these numbers feel fully included, we need to make sure we have 4 of them. And then to make sure this number feels included too, we need to include that 7. So again, to find the GCF, we use the lowest exponent we see on each one of those factors. To find the LCM, we use the highest exponent we see on each of the factors.
Ooh, can I try?
Fine.
Yay! All right. Whoop, all right. Move, screen.
Get out the way.
Oh, there we go. All right. So if we're looking at the GCF of these two values here, I'll keep pink, GCF. I'm looking at my 2's first. I'm looking for the lowest exponent to see what they both share in common. And what they both share in common is 2 squared. They both have at least 2 2's. Next, I'm looking at the 3's, and the lowest exponent is 3 to the power 4. Both values have at least 4 3's. The last number I'm looking at is a 5. And notice only the second number has a 5 there, but what we actually know is there's always going to be a 5 to the power of 0 here as well. It's hidden because 5 to the power of 0 is 1, and multiplying anything by 1 doesn't change the value at all, so we don't include it as written down in the prime factorization. But they do not share any 5's in common. So we could theoretically write 5 to the power of 0, but that wouldn't be fully simplified, because 5 to the power of 0 is 1, and 1 times 2 squared times 3 to the power of 4 is just 2 squared times 3 to the power of 4. So we don't actually have to write that at all. All right, for the LCM, we are looking at those same values, but now taking the greatest exponent, which seems somewhat counterintuitive, right? You're looking for the least common multiple, but you're looking for the greatest exponent. And I feel like a lot of people often get those confused, right? You're looking for the GCF and you're looking for the lowest exponent, and the LCM, you're looking for the greatest exponent.
Yeah, that's straight cray.
It sounds silly or counterintuitive, but as Mr. A explained before, it makes sense. So please don't get those mixed up. So let's start off by looking at these 2's. We're looking at for the highest exponent, which would be 2 to the power of 3. So we have 2 cubed over here. Next, we're looking at those 3's, and the highest exponent is going to be 3 to the power of 6. And then we're looking at those 5's. Remember that this first one here really is a 5 to the power of 0. And the highest exponent there is going to give us 5 squared. And that's our GCF and LCM of those two values. And again, we could evaluate that, but the instructions say that I don't have to, so I'm going to leave that as my final answer.
I will determine the GCF and LCM of this next one. And I will do so in darker, nice rich blue. Okay, heavily saturated. So GCF, wow, that almost looks black. It's really deep navy. Of those numbers, I can't include any 2's. I've got some 3's. The lower exponent is 4. I can't include any 7's. I can't include any 5's. But they do both have 11's, and I'm limited by the power of 1. There's my GCF third. And my LCM, my least common multiple, is going to include a whole ton of everything. So it's going to include those 2's to the 5. I'm going to include some 3's. I need to have 7 so that this number can feel fully included, like it's entirely welcome. I'm going to include 5 squared for this one's sake. I'm going to include 7 to the 4 for this one's sake. And then how many 11's? I need to make sure I include 4 11's so that this one can fully be at the party. Don't want to have it stand mostly outside the door. That's just awkward. And a fire hazard.
Ooh, my turn.
You know it.
All right, now we're carousing. Carousing. All right. So, looking for that GCF. Looking first at my 2's, we see that I have 2 to the power of 1 here, but of course the 1's not written because otherwise it wouldn't be simplified. But we know if there's no exponent, it would be a 1. So they both share at least 1, 2. And I'm not going to write that exponent down. Next, I'm looking at 3's, and this guy has 3, but this guy does not. So we're not including that in the GCF. As for 5's, we notice that this guy over here has 1 5. This guy over here has 9. Which means they have at least 1 5 in common. And lastly, this guy has some 7's. This guy has none. So we're not including it in the greatest common factor because they do not have those in common. So our GCF in this case is 2 times 5, which we could evaluate to be 10, but we do not have to in this example. For the lowest common multiple or the least common multiple, we're looking for the highest exponents on each of those prime factors that we have. First, we're looking at the 2's. This guy has 1 2. The other guy has 4 2's. So to make sure that they are fully included, we will say 2 to the power of 4. Get all those 2's in there. Next, we're looking at our 3's. This guy has 2 3's. This guy's got none.
Ouch.
But we still want to make sure that those 2 3's feel welcome. So we're going to include our 3 squared next. Taking a peek at those 5's. This guy has 1 5. This guy's got 9 5's. That's a lot of 5's. And they're all welcome here. So we're going to say times 5 to the power of 9. And lastly, we're looking at 7's. This guy's got 2 7's. This guy's got no 7's. But all them 7's are welcome. So we're going to include them in our LCM.
All are welcome in this place. Oh. Color options. I don't even know what I'm really feeling right now. Yeah, I'll take this. For my GCF. Can't include any 2's. Okay. So that's out of there. I can't include any 3's. Okay. Let's include some 5's. This one doesn't have any 5's, so I guess 5's are out. 7's? Nope. 11's? Nope. Do they have nothing in common? My
Whoa!
goodness. So what do I write here? Do I write like 0?
I don't know. What do you write?
Oh, I thought you were actually going to answer this one.
Oh, sorry.
It's all right. It's all right. We'll work on our banter a bit. For all that back and forth. It'll be great. They don't seem to have any prime factors in common. It's very, very, very sad. But every pair of numbers has one factor in common, and that's 1. 1 goes into everything. It's not considered prime, but it is a factor. And that's all they have in common. They don't have anything other than that. Maybe opposites attract and they can form a loving relationship, but I think it's good to have some commonality. I don't know. And for least common multiple, well, we need the 2's to be in there. At some point we need the 5's to be in there, and we need the 7's to be in there, so that this number is fully part of it. And then we need the 3's to be in there, and the 11's to be in there, so that this number is fully part of it. And that is, that last example, all done.
What?
I said that is that last example, all done.
Oh.
Yeah. You just gotta listen, you'll hear what I say. It's great. There's some practice. It's over down here, getting highlighted. It's pretty much the second best practice we've ever seen up to this point this school year. I'd recommend doing it because it is to your benefit. You'll want to make sure you're really familiar with all that stuff before we move on. And I think that's about it. Do you think we did a pretty good job?
Honestly, I'd probably give ourselves a round of applause. Oh my goodness, and so would everyone else.
Oh my goodness.
Thank you.
Oh my.
Thank you.
I never expected this.
I
they're standing. Oh my word.
Really, no, it was the students who did most of the work. Please.
No, I guess we did do a fair chunk of work too.
Okay, all of us.
We did a lot of work. We earned this. Yeah, no, keep going.
All right, no,
Okay.
please. Thank you.
Wow.
All right, so a round of applause to you, a round of applause to us, and we will see you in class.
Bye.